Hi there, and welcome to the second video in a three-part series covering linear regression. This lecture covers Bayesian linear regression. If you haven't seen the first lecture in this series, click on the link to check it out. The majority of the material of these slides comes from Christopher Bishop's book, but I recommend reading Kevin Murphy's book if you want to dive deeper into the material. I covered this notation in the first lecture, and it hasn't changed since then. So, go here if you need a vocal reminder. You'll remember from the basic regression lecture that we motivated most of the lecture through the use of this polynomial example, where we have a green true function and we have blue data points that are taken from it but are corrupted by noise. Again, for completeness, we have a set of input vectors x and associated output values z, and we want to try to approximate the function that generated them. We will use the following function y, which is a linear combination of the values of x. And to fit the function, we will seek to minimize the mean squared error between the function y and the target point z. Okay, so unless you were sleeping through the last lecture, we should all be on the same page so far. So with our sinusoidal example, we said that there was noise in the measurements. Let's model that noise as a Gaussian distribution, and that the mean of the Gaussian will be our function y, and our variance we will model as the inverse of the variable beta. It will be clear later why we modeled the variance this way, but just remember it's 1 over beta, or inverse of beta. So now we can write y as a distribution. We can write the probability of z given the input values of x, the values of y, and the values of beta. And by y, I mean the function of x and the parameter values of w. Okay, so what? Well, assuming that our data points are drawn independently and identically distributed, we can write out the likelihood function as we see in equation 6. Or, if we apply the negative logarithm to our function, or in this case, just the logarithm to our function, we can write it in this form. Why do we want to use the logarithm function? Intuitively, applying the logarithm function doesn't change the order or the position of the output values of the original function. That is, the maximum of the function is the same as the maximum of the log of the function. This is because the logarithm has the property that it is monotonically increasing. But there are other reasons to use the logarithm. For example, when working with Gaussians, it simplifies the math with the exponential. And also, it turns costly multiplications into summations. Okay, cool. We have a likelihood. Now what do we do with it? We maximize it. Starting from equation 7 on the last slide, I'm going to quickly walk you through the math. So firstly, we're maximizing according to W, so we only need to include the terms relevant to W. We can remove the beta term because it's just a scaling term. And finally, we multiply by -1 so that we were minimizing instead of maximizing. And voila! We get the same error function that we saw in the last lecture. What error function is that? Yes, it's the sum of the least squares. That means that the sum of least squares function is equivalent to assuming that the data has a Gaussian noise assumption. Let me repeat that. The sum of the least squares function that we talked about in the last lecture is equivalent to assuming that the data points have Gaussian noise. Now, we still have one parameter to maximize, namely beta. Let's follow the same process. First, we get rid of quite a few pieces that don't have a beta in them. Next, we rearrange the equations a little bit, and we get 1 divided by beta. Now you can see why we said we wanted to have the variance of our Gaussian noise distribution to be the inverse of beta, or 1 over beta. You'll also notice that to get the maximum likelihood for the beta, we use the maximum likelihood value of W. Now we can do this with the Gaussian distribution because the W is not dependent on the beta. In some other distributions, the parameters are coupled and you have to use an alternating update approach, but that will be covered in more detail in later lectures. Great. Now we have a maximum likelihood parameters for our model. What do we do with them? Well, now we can plug those values into our original equation and use that to make predictions. Cool. Now all of our problems are solved and we can stop paying attention to the rest of the lectures. Well, sadly, that's not the case. Remember, in the last lecture, how we saw how the high order polynomial overfit the data when we optimized it using least squares? Well, that was a special case of maximum likelihood. And one of the properties of maximum likelihood is that it overfits. So let's talk about a way for us to fix that problem. If you remember way back to the parameter inference lectures, there was a coin flip experiment where prior information was introduced to prevent overfitting. We're going to do the same thing here. But how does one choose a suitable prior? Well, that really depends on the problem that you're trying to solve. But an easy one to choose is a Gaussian. A Gaussian prior encourages small values because it puts more probability close to the mean. Also, since our likelihood function is already Gaussian, using a Gaussian prior means that our posterior will also be Gaussian. This is because a Gaussian is a conjugate prior for another Gaussian. The really cool thing is that since our posterior is Gaussian, we have a closed form expression for it. Okay, but what does all of this really mean? Well, since it's Gaussian, we know that the maximum of the posterior will be the mean of the Gaussian. You should remember that from the Gaussian lecture. If the prior becomes infinitely broad, that is, it becomes a uniform prior and not a Gaussian prior, then the maximum of the posterior is just the maximum likelihood that we discovered earlier. And if we don't have any data points, we still get a value from the posterior. It just happens to be based on the prior, as you would expect. Now that we've discussed things broadly, let's look at a more specific example. Let's assume that the prior that we have chosen is an isotropic Gaussian. If you think about it in two dimensions, this is just a Gaussian that has the same value everywhere, that is the same distance from the mean. So in 2 dimensions, if you were looking straight down on it, it would just look like a target. If you looked at the side, it would have the familiar Gaussian form. So in the last lecture, the variance of the Gaussian was 1 over beta. Here, we substitute 1 over beta, or inverse beta, for alpha, which is just called the precision parameter. Using that information and equation 15 from an earlier slide, we get a nice formulation for the mean and the covariance. So if you're staying with me, I want you to brace yourself. The next page looks scary, but it's all stuff that we've seen before. It's just a little condensed. Are you ready? Okay, here we go. As we saw earlier, the maximum a posteriori solution allows us to combine the prior and the likelihood to create a new error function for minimization. After applying the negative logarithm, we get E map, which doesn't look all that bad. So let's minimize it. This is just the full function from above written out. There's nothing new there. Okay, now all we've done is gotten rid of variables that don't have a W in them. A little bit of variable substitution, and voila. Wow, is that the same error function from the last lecture where we were doing ridge regression? What does that mean? No, seriously, see if you can tell me what that means. Say it out loud to yourself. I'll wait. That means that ridge regression is equivalent to the assumption that the weights W have a Gaussian distribution that models their uncertainty, as well as what we learned earlier about the likelihood function having a Gaussian distribution to model the uncertainty of the final target values. Let that soak in if you need it. There are other distributions which have conjugate priors and closed forms. We've already mentioned least squares and ridge and briefly mentioned Lasso. If you're interested in learning more about the other two or other forms, check out the mentioned reading in Kevin Murphy's book. Hopefully you were able to follow me through this lecture until the end. Up next, we'll be covering online methods for linear regression, both from the frequentist viewpoint and from the Bayesian. Thanks for watching and have a great day.